Hello and welcome to another session together. This is day 2 of Unit 9 where we continue to learn more about bonding. As it notes, if you haven't already done so, please watch the Zoom meeting from today. It just gives you a little bit more context and also reviews some stuff from day 1 that will be helpful moving forward. So assuming you've seen that, let's go ahead and jump in. Our objective today is for you to be able to interpret and draw molecular structures. Go ahead and turn that into your EQ for today so that you have an idea of what you should be able to answer by the time you are done with this video lecture. The reason I want you to be able to draw and interpret structures is because as a chemist, knowing what a compound looks like in terms of how the atoms are organized helps us understand a little bit more about that compound, and that's what we want to be able to do. So we're talking about molecules today. So just a reminder that a molecule implies that there is covalent bonding happening inside those atoms or between those atoms. So we got our share bear here to remind us that a covalent bond is when you're sharing electrons. We are going to think about electrons coming in pairs. If you learn more chemistry, you'll see that sometimes that doesn't always happen. But for now, we're going to think about, in a molecule, electrons coming in pairs. So that means that a covalent bond always will represent 2 electrons. So this is usually, and again, there's an exception to this too, but we'll talk about the rules for now. One atom brings 1 electron and another atom brings a second electron, and together those 2 electrons create that bond. So one nucleus is attracting its own electron and the other electron from the other element, and then the same thing. The second element is attracting its own electron and the electron from the other element. That connection creates that covalent bond. So if you have a single bond, that's thought of as 2 electrons. A double bond then would be 4 electrons because it's 2 pairs. A triple bond then would be 6 electrons, 3 pairs. But then sometimes, because of the electrons available, atoms don't have to share everything. So you can also have something called a lone pair, which I realize kind of sounds like an oxymoron. How can you be alone and in a pair? But what this means is that one lone element keeps that pair of electrons. It's not being shared. It's not a covalent bond. It's just its own electrons to make it stable. But the point is that it didn't have enough electrons by itself to be stable, so that's why it started making bonds at all. But it didn't have to make all 8 electrons stable, that kind of idea. So you'll see more about that when we start practicing this. So what I'm going to do first is just to show you some structures, and let's just go through sort of the general format. We already know what the letters mean. We know that H is hydrogen, N is nitrogen, or you could look it up, but collectively that's called ammonia, which is a common fertilizer. Water, we of course know what that is, and then hydrogen fluoride or hydrofluoric acid, used in lots of industries for dissolving things, a really, really tough solvent, that kind of stuff. Anyway, but I want to talk about what the rest of this stuff means. So we represent a bonded pair of electrons with a line. So we will know now that this line means that you have 2 electrons, that's 1 covalent bond, and then dots are representing our unshared electrons, so our non-bonded electrons or our lone pairs, like we just defined it. So like this nitrogen has 3 bonds and 2 electrons that are not being bonded. This oxygen has 2 bonds, which would be 4 electrons, and 4 electrons that are not bonded. This fluorine has 6 electrons that are not being bonded, and it has 1 bond or 2 electrons that are being shared. The reason there's a certain number of lines and dots is because every element is trying to stay stable. The reason that it made this compound in this format is because this is a way to make each atom stable and create a molecule that then can do something. So we are still following the octet rule, meaning that there's 8 electrons for most elements. So for example, this nitrogen has 3 bonds, which remember is really 6 electrons, 7, 8. So this nitrogen has 8 electrons. This oxygen has 4 in the bonds, and then 4 in the lone pairs. So total, that's 8. This fluorine has 5, 6 unshared electrons, and then 2 shared electrons. So total, that's 8. But then you might notice, oh, wait a second, hydrogen doesn't have 8. There are a few exceptions to the octet rule. Hydrogen is the one that you will see the most, and it only needs 2 electrons to be stable. Think about why that might be. Think about where the octet or the 8 rule comes from. Remember, it's from the S and P sublevels being full. So the nitrogen and the oxygen and the fluorine, they want to have a full S and P sublevel. That's where the 8 electrons come from. But hydrogen doesn't have a P sublevel. There isn't a P sublevel in energy level 1. It's too little. The nucleus is too little. It can't hold on to that many electrons. So hydrogen is stable when just the S is full. Well, S can only hold 2. So notice that all the hydrogens just have 1 bond. That's 2 electrons, 1 bond. 1 bond. So this hydrogen, all of the hydrogens are stable when they only have 1 bond. So those are the things I want you to be aware of when you look at a structure. Go ahead and do a level 1 question so far. Pause the video if you need to, or think for a little bit. What will be a good level 1 question? Think about what you've done so far. Something straightforward right from the notes. All right, in our next section, I just want to do a few examples of structures. You don't have to write this down. Just go ahead and listen to this. We'll pick up the notes in a little bit. What I want to do is just kind of walk you through some of the chemistry going on to make molecules. Let's start with diatomic hydrogen. Pretty simple molecule, just 2 elements, and total in that molecule, there are 2 valence electrons available. Where did that come from? Well, hydrogen is in the first S column, which means it starts with 1 valence electrons, or think of it the electron configuration, 1s1, 1 valence electrons, but there's 2 hydrogens, so total you have 2. There's only 2 valence electrons available to make 2 hydrogens stable. So this is how they know they have to make a covalent bond. But if they do a single covalent bond, that is 2 valence electrons. That will make hydrogen stable because it only needs to fill up the S sublevel. So it looks like this. Hydrogen has 1 electron, hydrogen has 1 electron. But if this hydrogen attracts both of those, it creates that covalent bond, which we represent with a line. So now this is the stable structure or structural formula for hydrogen or diatomic hydrogen. So 2 valence electrons, because this hydrogen has 2, this hydrogen has 2. This nucleus is attracting 2 electrons, this nucleus attracting 2 electrons. So total, you get that stable molecule. So again, creating this visual, instead of just calling it diatomic hydrogen, H2, now we get a visual of what's going on, the chemistry, the structure of it. Let's continue with that diatomic idea, and now let's do diatomic oxygen. Oxygen starts with more valence electrons. So if you have 2 oxygen, you can actually add up to 12. Because if you look at where oxygen is, it's in the 4th column of the P block. So if you add those 4 plus the 2 from S, you get 6 valence electrons for each oxygen. So total you get 12. Well, in order to make both atoms stable, they can't just take 6 and 6 because that is not stable. Or if one takes 8 and the other has 4, that's also not stable for both of them. So they're going to have to be more creative and they're going to create a double bond. So here's how the 6 electrons start, right? If they just share 1 pair of electrons, then that's still just 6 electrons each and it's not stable. But if they share 2 pairs of electrons, like is being shown here, there's 4 electrons being shared and then 1, 2, 3, 4 electrons for this atom. Total is 8. 1, 2, 3, 4 plus the 4 shared 8 electrons for this atom. And then total, there's only 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the rule is you're trying to get everything to be stable, but you can only use the pieces that are available. In this case, there's 12 electrons. So they had to be a little bit creative in order to create a stable molecule between the 2 atoms. Continuing with that diatomic, let's do one more example just to kind of see the chemistry going on here. So diatomic nitrogen would be N2. But if you look at where nitrogen is on the periodic table, it's only in the 3rd column of the P block plus the 2 from the S. So total, there's just 5 electrons from each nitrogen. So then that equals 10. So if they start with 5, so here's your Lewis dot diagrams from your 5 valence electrons, what you end up with is sorry, just a second. Let me come back here. Okay, so what you end up with is you have 5 valence electrons, 5 valence electrons. So if you might notice, well, wait a second. Here's a electron by itself and they want to have pairs. Here's an electron by itself. So if those 2 would get shared, that means that this nitrogen would have 1, 2, 3, 4, 5, 6. Oh, but then if you just have 1 bond, that's only 6 electrons total for that nitrogen, so that's not stable. So what happens is they have to be more creative with their sharing. So since there's only 10 total, they're going to make a triple bond. So if this nitrogen shares 1, 2, 3, 4, 5, 6 between the other nitrogen, it then only needs 1 lone pair total to make it stable. And then same thing with this. So then that's how you get 2 atoms to be stable with only 10 electrons total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 electrons total. Both atoms are stable. That fits the rule. So then this is a stable molecule. So that's kind of the idea of what we use or what we think about when we're trying to draw structural formulas. Go ahead and do a level 2 question and then we'll move on. All right, so then the last piece of this today is actually drawing the structures yourself. So let me give you some guidelines of how to do this, and then you can start practicing this on your own. Show you the chemistry that you know. The first thing you double check would be kind of like what we learned in day 1 or what we reviewed in the Zoom meeting today. If you're dealing with ions or an ionic compound, remember you automatically give all the elements 8 dots, you put brackets around each element, and you put its charge. And then you balance the charge. And then remember, you can only put pluses and minuses next to each other, which is how you end up with kind of like that 3D structure that would be really organized, which is kind of one of the important things about ionic bonds or ionic compounds or formula units. So like the bell ringer this morning, which was strontium and fluorine. So we connected the 2 fluorines with the 1 positive 2 strontium. We balanced the charge, 8 dots bracket. So that's one thing you'll look at. If you've decided it's a covalent structure, then what you need to do is you need to add up all of the valence electrons of the elements involved. So how many electrons are available to make this molecule? Then, because it's a compound, you know that the atoms have to connect. So you have to put at least 1 bond between all of the elements, and that gets you started. Remember, looking for that, looking for something to be kind of in the middle, if possible. And then based on how many electrons you had available, you add in lone pairs or multiple bonds as much as are needed to make each atom stable. And to be stable, remember that for most elements, that's the octet rule, 8 valence electrons, except that exception of hydrogen that only needs 2. And really think of it like a puzzle. So you've got your pieces. What are the elements? How many valence electrons? How many bonds? And then you kind of just move stuff around until you get the stable picture of that molecule. All right, let's try some examples to see if this is making sense. We're going to do dichlorine monoxide. And remember, think of it kind of like a puzzle. Let's think through what the pieces are. And let's do dichlorine monoxide. The first step is to see, is this an ionic compound? And they're not. Chlorine and oxygen are both pretty close to each other on the periodic table, meaning that their nuclei would be pretty similar. So neither one is strong enough to pull an electron away. So this is not ionic. So then that means step 2 was to add up the total number of valence electrons. Well, chlorine is here. So if you count backwards or start from here and go forwards, 1, 2 from the S, and then 3, 4, 5, 6, 7 total, because 5 from the P block, 2 from the S. So chlorine has 7. Oxygen is here. If you count backwards, 1, 2, 3, 4 from the P block, and then 2 more from the S, so that's 6 total. So then for the valence electrons available, 2 chlorines each have 7, and then 1 oxygen has 6. If we add that up, there are 20 valence electrons to make a stable molecule, a whole molecule. So now the next step said, well, we have to connect these pieces. So we're going to look for a central atom. And your hint is that your central atom is always going to be what you have least of. So since I have 1 of these and 2 of these, the atoms and molecules try to arrange themselves to be symmetrical. A lot of times nature tries to be symmetrical if it can. Sometimes it can't. But in this case, we're going to put oxygen in the center, and then we have to connect them. Otherwise, it wouldn't be a molecule. So at this point, I have 2 bonds and I have 4 electrons that I've used, which means I have 16 electrons left. So the next thing to try is just put lone pairs in and see if everything would be stable. So for example, this chlorine already has 2, so it would need 6 more electrons. This oxygen has 1, 2, 3, 4, so it would need 4 more electrons. And this chlorine would need 6 more, the same as this. So if you do that, so I've got my 8 electrons here, 8 electrons here, 8 electrons here. Let's add up. Do we only have 20? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So that works. All the atoms are stable, meaning they all have 8 because there's 2 here, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen, and this chlorine matches this chlorine. So all of the atoms are stable, and we only use the number of electrons that were available, not more, not less. So you have to use all the electrons are available, but you can't use more than that, and you can't let them disappear. So this would be the structural formula for dichlorine monoxide. So as a chemist, this would start to tell us some things about, okay, would this dissolve in water? Would it have a high melting point? Would it conduct electricity? These are the kinds of things we care about. So then if we wanted to use this as a cleaner or in some sort of pharmaceutical, would it mix with water? Would it dissolve in our body? Would it clean off oil? These are the kinds of reasons we might care about the structure, because that's that's going to help us understand the chemistry of this compound. That's why we care. That's where we're going. Today, though, it's really just about drawing. So let's start there. Let's go back and do another example. How about sulfur dioxide? Once again, the first thing we check to see if we're dealing with ions. We are not. Sulfur and oxygen are really close on the periodic table. Their two nuclei are too similar to really create an exchange of electrons. So that means the next step is we have to add up the valence electrons available. Well, look at sulfur and oxygen are actually in the same column. So they both have the same number of electrons. Well, how many is that? Go back to the beginning. 2 from the S and then 1, 2, 3, 4 from the P. Total, that means you have 6. So all of them have 6. So if we add that up, that's 18 valence electrons available to make this whole stable molecule. Step 3 says you have to connect them. So there has to be at least one connection between all of them. We look for a central atom. In this case, it'd be S, and we connect it with our oxygens. So now, once again, we've used 2 bonds to connect the pieces, trying to be symmetrical if we can, which is 4 electrons. That means we have 14 electrons left. Well, if we did like we did last time and we just spread out the electrons, this atom has 2 electrons right now, so it needs 6 more. This sulfur starts with 4, it needs 4 more. This oxygen starts with 2, it needs 6 more. So if we just do that, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Well, that doesn't work because remember, we only have 18 electrons allowed. So that means that this structure is not accurate. If we are allowed less electrons than when we just spread them all out, this tells us we have to have some multiple bonds. So this structure is not accurate. We need to put a double bond in somewhere. So I'm going to put a double bond here. So instead of having this as a lone pair, I'm going to make it another shared pair, which means I can take off one of these lone pairs from sulfur, and then that's going to get me my 18. Let's double check. So I have 2, 4, 6, 8, because remember there's 2 in every line, 10, 12, 14, 16, 18. So I've got 18 valence electrons, but we also have to double check if all the atoms are stable. This oxygen has 2 right here, and then 3, 4, 5, 6, 7, 8. This oxygen's good. Sulfur has 1, 2, 3, 4, 5, 6, 7, 8. Sulfur's good. And then oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is good. And just so you know, it really doesn't matter if the double bond is here or the double bond is here. It actually kind of is like flipping back and forth because remember, electrons are moving. So in this example, the double bond here and the double bond here would be equal. There's some compounds where putting the double bond in a different place will change the structure a little bit, but that's not something you need to worry about. For now, just be aware that if you learn more chemistry, you might have to be picky about where you put the double bond. But for our example, the double bond is just as equal here or here, because if you put it here, you would just put this lone pair of electron then to balance out this oxygen. So just know that for now, the double bond just kind of moves around because electrons move. Okay, so then this works. All of the atoms are stable and we only have the number of electrons available, not more, not less. So this would be the structure of sulfur dioxide. Let's do one more to kind of cement this and then maybe see one a little bit different. CO3, but then there's this -2 here. So when I look at it, well, I know that that -2 means it's an ion, but C and O are not ionic bonds because they're too close to each other. Neither element is strong enough to pull an electron away. So that means that even though this looks different, I'm going to start it the same way I've done all the others. Start by looking at the number of valence electrons. Carbon is here, so 1, 2, 3, 4 for carbon, and then each oxygen from before, like we did, is 6. So that means if I add that all up, I've got 3 oxygens, they all have 6, and then 4 from the carbon. That looks like 22. But remember, there was that -2 charge on this compound. So then we got to remember, okay, a negative charge, the reason you become negative is if you gain electrons. So that means instead of 22 electrons, this compound got 2 extra electrons from somewhere else. So instead of 22, there's really 24 electrons for the molecule. But wait a second, here's maybe where you remind yourselves, wait, this isn't a molecule. This is called a polyatomic ion. So this is maybe a term you remember from before. This is really carbonate. So carbonate only happens if it gains 2 electrons from somewhere. We're going to just draw this structure for now, but then realize that means that this whole structure could connect with something positive. So let's keep going. So I've got my 24 electrons. We're going to keep going the same way. You find your central atom and you connect it with one of each of the elements. So then I've got carbon with 3 bonds around it, and that means that I've used 6 electrons. But remember, I had 24 total, so now I've got 18 left. Well, if I spread out my 18, because right now this carbon has 6, and then this oxygen, each oxygen only has 2. So really, each of those oxygen needs 6 more. So if I put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Hey, I'm all good. All the oxygens are good. Oh, wait, but then there's not enough electrons left for carbon because carbon only has 6 right now. It needs 2 more. So remember, if you have less electrons available than just spreading them all out, that means you need to have a double bond somewhere. So I could put a double bond on any of these oxygens, and then I spread out the rest of the electrons that I have, and then that will make my stable answer. Sorry, just a second. I have to go back and come out of this. I don't know why it keeps doing that. Okay. So then if I put a double bond here, that means now the carbon is totally stable. It has 8 because it's got 4 bonds. This oxygen now has 2, 4, 6, 8. That's good. This oxygen has 2 here, 4, 6, 8. That's good. This oxygen has 2, 4, 6, 8. That's good. And then let's double check. Do we only use 24 electrons? 2, 4, 6, 8. 10, 12, 14, 16, 18, 20, 22, 24. Yep. But remember, we only got 24 because this is a polyatomic ion. So don't forget the brackets and the charge. So brackets with that -2, because if you leave off the -2 in the brackets, this is not what CO3 would normally look like. All right, and then we check our work. Are all atoms stable? Yes, they were. And did we only use the number of electrons available with that charge? Yes, we did. So then this becomes a stable polyatomic ion. It is still covalent bonding inside something that has a charge because it gained electrons. So again, the idea is that this whole thing would now try to bond with something positive, like maybe sodium carbonate or barium carbonate or something else. And then you would just do barium with 8 dots and a +2, and then that would balance this out. But that's kind of looking ahead of what else you might do with this kind of thing. But for now, I just wanted to give you an idea of drawing these structures. Okay, go ahead and do a level 3 Costa question. Make some sort of prediction or judgment or something like that. And then you're going to do a summary. Remember, your summary should answer the EQ that you wrote. All right, so now with all of that new information of trying to understand more about the chemistry going on by drawing structures, here's what I want you to do today. If you didn't do so already, go back and do your questions and summary because that's going to help you process the notes that you just took. There is a practice assignment on Schoology. It's called the Molecular Structures Practice. So put that into Notability and try those. So use your notes from today and try interpreting and drawing structures on your own. There are some unit practice problems, and remember, those are nice because you can check your answers, and then let me know if you have questions, of course, and then I'll see you at our next Zoom meeting. All right, thanks for joining in. Have a great day.